The idea was this would be up here so everyone could read and laugh. But I want to get you all to lunch, so maybe we can look at this later. So my talk, as was wonderfully stated, is about a game of theories of all these languages we use. I want to quickly take a moment, though, and mention the company that I work for. They helped me come here today. The company is called Tallwave. They are an agency based out of Arizona, US. And what we do at Tallwave is we help brands navigate complex user problems so that they can disrupt their market. And a lot of people like to use this word disrupt, right? It's very popular. But it's not the word itself that matters, it's the story behind it. And Tallwave's story is a true force for change and upending the status quo that some of these industries face. And just as our story at Tallwave drives our decisions and drives what we create and how we create, so do the languages that we all use have a story behind them as well. How this ties into Game of Thrones is similarly, in Game of Thrones, there are some characters who are awful and some who we might say is a good guy, but they all have reasons for making the decisions that they do, right? Sometimes they make you even feel bad for someone who is a bad guy because there is a reason they became the person that they are. I want to cover a couple of concepts before we get going, and I'm sorry. The internet is always wonderful, because I'm sure, well, I know there is at least one person in this room who, like myself, did not study computer science in college. And so for that person, I want to make sure they know when some of these concepts come up throughout the talk, you can be with the rest of us and understand. So the first concept, I'm borrowing a wonderful graph by Vaidehi Joshi. I recommend you look at her Medium blog series on CS. It's wonderful. So this shows the difference between linked lists and arrays. Now, if you are like me and learned to program with something like Python or Ruby, you have been lied to. An array in Ruby is not an array in computer science, and a list in Python is not a list in computer science. So let's get a handle on what those mean at their base level. So arrays are static. They need a continuous block of memory. This is great because you can access by index. This is not so great because if you want to add or subtract things from the array, you have to remake an entire new array in a new contiguous block of memory. And linked lists are sort of the opposite, right? They are dynamic. They don't need to be contiguous because each item points to the next item in the array, so it knows where that item is in memory, so they can be spread throughout. This is great because you can add to the beginning and the end quite easily. You don't have to reallocate memory. However, it is very challenging, very difficult to access by index because you would have to start at the beginning and follow each pointer to the next item. So they each are used in their own way. The next concept is locks and thread sync. This is used in concurrent programming. It's this concept where you might have a thread that is executing some functions and is using some variables that another thread also needs to use. And you don't want those threads changing those variables at the same time. So you would need to lock one thread or the other and then unlock them when it is safe for that thread to use the variable. That might sound complex, and it's because it is. And so the concurrent languages we'll look at have found ways around this so you don't have to always be locking and unlocking and trying to remember which order your threads need to access variables in. So let's get started with Ruby. There's about 7 languages we're going to go over. It's going to be a very quick high-level overview, and hopefully you will have as many answers as questions at the end, and it will be fun, and then we'll go have lunch. So Ruby was created by a man known as Mats, and it was created because he wanted programmers to have fun. And this is evident in a lot of the ways that Ruby works. So one of the ethos or values of the Ruby community is this thing called MinSwan. And MinSwan stands for Mats is nice, so we are nice. And it drives the Ruby community to be welcoming and wholesome and Nice. It doesn't always work. Communities are made of humans, but this is a thing that is a part of Ruby and does welcome especially beginners and encourage them to move forward. Mats also wanted to make Ruby natural, not simple. So you can see this in Ruby syntax. It's supposed to read sort of like a sentence. And so he sometimes, he also allows a lot of flexibility, as we will see, that is not always simple, but does give the programmer more ability to have fun as he values. So everything is an object. Mats wanted to make a language that was more object-oriented than Python, so he made everything an object. And one way this plays out is that Ruby does not have incrementers or decrementers. You cannot do, I++ or I in Ruby, because these are functions that you use on variables in C, not on objects, and everything in Ruby is an object. So you don't have decrementers. How Ruby implements arrays is very interesting. Like I said, it's a lie. It's not an array like we just looked at. It's kind of a mashup of an array and a linked list. And to get around, so you can add to the beginning and the end and take from the beginning and the end and access by index and do all these things. And then to get around this problem of needing to recreate the whole array every time you add something or take something away, Ruby actually implements a minimum array length that kind of goes in stages. So for example, when you create an array at first, as long as there are less than 3 items in the array, your array in memory has a length of 3. So when you add a second item and a third item, that array does not have to reallocate memory. Once you go above 3, then it jumps again. Now, in the background, you actually have a block of memory of 20. And then if you go above 20, then it jumps again to 37. And so it's doing this kind of to save memory in the long term so you can add and subtract with a little bit more flexibility there. And flexibility is the name of the game in Ruby. One aspect of Ruby that is not so great is this concept of monkey patching. And that is where you can actually, I'm going to move this. You can completely overwrite a method in a class that you pull in. And so this is available in other languages, right, like Python, JavaScript, but it was really accepted in the Ruby community because of this value of flexibility and creativity and being able to make whatever world you want, with your programming language. And this becomes really problematic, especially in open source, when, for example, I had to troubleshoot something, and I was using a gem or a Ruby package, and it had imported a class from another package, but had monkey patched it, had overwritten that class. So it was completely different in how it worked, and I guess output something of the same name, but it was, it was all different. So then I thought, okay, well, I'll look at this class. Well, the problem was that had also imported another class from another package, and monkey patched that. And this went up for 4 levels. And so it was very frustrating to troubleshoot, and that is kind of the weeds that you can get into with Ruby. However, it's a part of the language because Ruby wants you to have the flexibility of creation. Again, they want you to have fun and to be able to not be inhibited by rules or, regulations when you are coding. This tweet kind of sums up the Ruby mentality a bit. Pythonists are all explicit is better than implicit, and Ruby says, look at me, I made a bong out of this hairdryer. So, now I think Pythonistas have fun too, but it's still a good tweet. So now we're going to look at Python, and Python has something called a Zen of Python, and that kind of sets the tone for what people in the Python community value. We're not going to read the whole thing, it's quite long, but a few we'll look at are the first 5, which is beautiful is better than ugly, explicit is better than implicit, simple is better than complex, complex is better than complicated, and readability counts. And you see these right away with readability counts. The spacing in Python is very important. So this means that a function follows it, And everything indented is part of that function. And once you stop indenting, you have stopped adding things to the function. So it's very clean and pretty and easy to read, and that is the value that Python holds. Now, how I alluded to it a bit, how Python implements lists is sort of also a bit of a mashup of linked lists and arrays you can access by index and add to the end. It's not quite as easy to add to the beginning of a list, but Python has ways around it. But I want to point these out. I'm leading up to a unique aspect of Python. So lists and tuples are pretty similar in how they work, access by index, add things. However, the difference is that tuples have immutable types. So the item, if you create this tuple, you cannot replace this one with something else. It is immutable. And that comes into play with how Python implements like a Ruby hash map or something. So they have dictionaries, and the keys in dictionaries have to be immutable data types. So you can use a tuple as a key in a dictionary, right? So there's some kind of flexibility there a little bit. But the reason why it's very important that these dictionaries have immutable keys is because that supports a quick lookup when you are looking through a dictionary for something. And that is important because Python does not have case or switch statements. And this is intentional, right? It kind of goes back to, another piece of the Zen of Python is if the implementation is difficult to explain, you probably shouldn't do it. So I want to read this quote by one of the Python core developers. He said this when rejecting one of the many proposals to implement and add case switch statements into Python. People have tried to add it. They have been turned down. So this developer said, without having a way to declare named constants, there is no way to generate an efficient jump table. So all we would be left with is syntactic sugar for something we can already do with if, else chains, or dictionaries. And that is, in fact, the Pythonic way to implement or to operate something like you would with a case switch. You use a dictionary and lookups as a lookup table. And another example of how Python does not add things when something else in the language already serves that purpose is with multi-line comments. There is already something, multi-line strings can work as multi-line comments. They don't generate code. And so this is actually the creator of Python. Guido, he's still quite involved in the community. And so this is what he says. It's already there. Use it. We don't need to add more complexity that is unnecessary. Now, Python has, there is a saying in the Python community, I'm not sure who it's attributed to originally, but it goes, Python is the second best language for everything. Which is wonderful, if you develop in Python, you love that it can be used for so many things. You know one language and you can do so many things, data science, machine learning, there are so many applications. But sometimes you want to specialize a little bit more. And there was an example with a company named Stream, and they used to use Python for serialization and ranking and aggregation. They instead moved over to the language Go, or Golang. And the reason they did this is kind of true to the reason Go was created. So the reason Stream moved was they wanted a language where it was quick to onboard new people, and that, of course, was fast at those things that were aggregation and serialization. So a language that was quick, easy to understand, and easy to train new hires. And those are conveniently all values that Go espouses. So a quote from the Go blog reads that they wanted to have something that was easy to build, simple, reliable, and efficient software. Now, Go was created by developers at Google, so Google could use it, so that may make sense to you. Another thing they valued, actually, was that it could be used across dispersed teams that were coordinating only loosely. It's another rough quote from their blog. And again, you see that is what Google needs. They have large teams of engineers who are coordinating only loosely, and they need to be able to onboard people quickly as they move across departments. And so they implemented things very simply. Go is primarily a concurrent language, and how you create a concurrent thread is you simply take any function and you put Go in front of it. And now you have a thread. Congratulations. And this is quite easy to onboard someone with, right? And then how you can maintain concurrency or kind of get around the locking problem is when you pass a value to a channel, or sorry, you create a channel and you pass a value into the channel. You can also use this to pass Go routines into channels. And channels are, the processes that house these threads, and they automatically, in terms of that locking problem we discussed, the sender who is sending a message to the channel does not send until the receiver has, said that they are ready to receive. And likewise, the receiver does not, receive something unless the channel has said they are ready to send. So both parties have to say, okay, we're ready, and then messages can pass between them. So you don't have to explicitly state, hey, lock, unlock. It's already set up for you there. Now, I wanted to talk about how Go implements arrays because they do it correctly. An array in Go is an array in computer science. It's an immutable, set of memory, and slices are what you would know of, in Python Ruby as like a list or an array. So they are built on top of arrays in Go, and they do all the things you would want. You can add and take things away, access by index, all these wonderful things. And then maps are also kind of this lookup hash table. But I do like that they kept arrays in there true to their form. Go also really values that you know what to expect and you plan for it. Let me break down a couple of things here so that we're all on the same page before we jump into this. So this colon is a shorthand in Go syntax. So in Go, you have to declare a type that your variable is. But if you are inside a function, you can use this shorthand syntax, and instead of explicitly stating the type, you can tell Go, hey, just infer the type. Whatever type this is, assign that type to this variable, and do it all in one shorthand so you don't have to declare types so much if you don't want to. So that's what's happening there. Now the rest of this, so in Go, you have the option to expect an error or expect an OK. And you can handle this a couple of ways. So like here, you could expect a response, and if you get one, then you assign it to the variable and you handle that. Or if you expect that you might get an error, because that happens sometimes, then you would assign this and then handle an error in the next line. This helps, avoid some of the extra code around, like a begin statement in Ruby or something where you have to have this framework around possibly getting an error, those try statements and things. This is a bit more concise. And then down here, we actually don't care what value we get back. You can say, hey, whatever value I get back, throw it away, it doesn't matter. I only care if it succeeds. If it succeeds, we're good. And so Go allows you to know what you expect and plan for it. And it also will not compile without unused imports. Someone should tell NPM about this. This is another aspect of Go that shows they value efficiency and lightweight syntax, that lightweight code. They don't want you to bog down with anything that is unnecessary. Another, in regards to that as well, they want you to be able to onboard people quickly. One way to do that is to make sure everyone uses the same formatting of their code. So there is a package in Go called Go format. And if your team requires you to use this and you run it, after when you compile each Go package, it will format your code for you. If you used spaces, it will change them to tabs. And indent your code so that everything is homogeneous, everything looks the same, and you don't have those random spacing errors maybe when you're pulling code down that your teammate pushed up. So that can be quite helpful, again, on large teams that are coordinating only loosely and may not have time to share all their linting files or what have you. Now, one thing that Go does not have is generics. Now, I didn't cover this at the beginning. We can go into it a bit now. As I mentioned, Go requires that you declare a type. A generic, which is not in Go, this is fake, do not do this, is when you say, okay, I have to declare a type because this language makes me declare types, but I don't know or care what type this is, so it can be any type. If you are familiar with TypeScript, right, you can actually put any here, and it does this, or some in the language we'll look at next, you can use a capital letter like this. And so this does frustrate some Go developers, right? Generics can be very useful. However, similar to Python's case and switch, loyalty or avoidance of it, the Go development team maintains that adding this would introduce unnecessary complexity, and that you can already work around this with ways that Go already has in it. So maybe sometime in the future, they might add generics, but for now they're not in a rush because you can do it another way, and they don't want to add unnecessary cruft on top of this language. They want to keep it lightweight. Now, as I mentioned, there is a language that also does concurrency, that lets you have generics, and that language is Rust. And Rust is awesome. I just started learning Rust within the last month, and I am infatuated. It is really, really cool. So the founding ethos of Rust was that they wanted to give developers the power to do things on more of a closer to the processor level, like C allows, but still protect us from all of the mistakes that we make every day. So the compiler in Rust is very robust. It catches a lot of problems that might sneak by in other languages. So there's a lot of safety net in Rust, but they still allow you at the base a lot of freedom. Now, they are a concurrent language, as I mentioned, and how they handle that is through a concept called ownership. This is a bit unique to Rust, so we can break it down here. Ownership is this concept of owning a variable or something that can change. So as you see here, if we instantiate a variable, and then we pass it to a function, this function now owns this variable. Until this function passes it back to us or sends it somewhere else, this function owns this variable. So if we then try to change or do anything with the variable in any way later on, this will produce a compiler error. So another example. So how this works with working with channels is, so we have some channel of our concurrent threading going on. We create this variable, and side note, this mute means that this variable can be mutated. Variables in Rust are immutable by default, but you can say that you specifically want to mutate something. So we have a mutable variable, and we send it to a channel, and now this channel owns this variable. So if we then try to send this variable somewhere else, we cannot. This also produces a compiler error. So this is how they solve that, that locking problem. Only one channel can own something at any one time, and they have to explicitly pass ownership before anything else can mutate or use that given variable. Another unique aspect to Rust is how they handle garbage collection, and this is kind of powered by that concept of ownership that we just discussed. So garbage collection in most languages, it either runs at kind of regular intervals, or maybe once the memory starts to get full, this garbage collector will run, and it will look for all unallocated variables. So if you create a variable within a function and only use it within that function, and then that function is over, it will look for those variables and deallocate the memory so that that memory can be used again for something else. Now, Rust does this all the time, automatically, based on this concept of ownership. So once this function ends, it no longer owns this variable. And so now Rust knows that it can deallocate the memory that was assigned to creating that variable, declare. And this is quite useful because Rust also wants to take over the world, which we'll get to in a minute. And so this helps Rust to be somewhat invisible as it is added into other code bases and other languages. One thing I want to cover before we get into the infiltration of other code bases is that Rust does not have a null, which I had not seen this before anywhere else. And one of the driving reasons for this is the man who originally implemented this null has called it his billion-dollar mistake. And Rust wanted to avoid that. And it's similar a bit to Go in that Rust wants you to know what you're expecting and plan for it, and that there are many examples of that in Rust, but the one we will focus on is this absence of a null. So if you do something in Rust and you do not use this option, so this option expects either something or nothing. That's all. So you would use this if you expect that a variable or a function might return something that is null, then you would use this. You would specifically say, hey, I might get a null back, and that's okay. But if you don't explicitly state this in any case where you might get a null back, maybe you wrote some bad code, it happens, the compiler will catch that and throw an error. If it finds something where you could possibly get a null back on some edge case, but you have not used option, then it will throw that error. So that's kind of one of those examples we talked about where Rust has these checks and kind of this guard with the compiler around all of the mistakes that we make quite commonly. So also you don't get those errors, right, in Python, Ruby, JavaScript, like, oh, cannot read property X of undefined, and then you have to figure out what undefined is. You don't have to do that here, which is quite nice. So, as I mentioned, Rust wants to take over the world. One of their kind of founding ethos from a few years ago was Rust once, run everywhere. And this is a play on the Java, saying that is, what is it, write once, run everywhere. Java and the Java virtual machine, they wanted to also be everywhere. They nearly succeeded. Rust, in the same way, wants you to be able to write Rust code and run it everywhere. And so again, that garbage collection, not keeping memory around more than it needs to, it wants you to be able to use it within like a C code base or even Python, Ruby, JavaScript, all these other code bases, and not be noticed in terms of memory or anything extra. So it is really neat, and I'm excited to learn more about Rust as I go. Another concurrent language that also plays on the Java saying is Erlang. And Erlang's thing is write once, run forever, never die. Joe Armstrong is, of course, one of the lead developers that created Erlang. And we'll spend just a couple of slides here, but I wanted to point out how they handle that locking problem. And that is through message passing. So every processes in Erlang are isolated in memory, and when they pass variables to each other, they pass a copy of that variable. So, and then the process that receives it decides what to do based on that information that it receives. But this is useful because if a variable is sent to one process and it handles it in a bad way, then it can die. Erlang espouses this notion of if you have a decaying limb, cut it off, don't let it affect the rest of the body. And this is useful and kind of supports how they do error handling. So when a process dies because typically, like if a process dies unexpectedly, something horrible happened, then it sends an error message to its parent process. Now this is wonderful and also overloading. So it's wonderful, right? Because if there is a process that is could possibly break the system, it kills itself and it dies. You don't need to worry about it infecting the rest of the system. However, it's going to keep trying to restart and fix that error. So like in cases like this, you may get an issue where if it restarts and restarting fixes the error, great. But if it restarts and then receives the same message from, maybe another process was sending it a message that caused it to crash, and that same message has the same reaction that this, the receiving process takes, then it dies again. So this can clog up your logs, and I'm sure we're all familiar with that. But it is still quite useful with the, the exiting and the reason. And I do want to give a quick shout out to Erlang before we move on. I was very early in my career with debugging an Erlang problem, and I figured out the solution by actually going into Erlang source code and reading it, and then figuring out what was expected, how to handle it, all of this. And that was very nice and kind of rare. Like, I've been in, some source code bases that are a bit dizzying, but Erlang's I found it to be quite clean and very readable, actually. So that is Erlang. So these are a lot of concurrent languages, and they all handle concurrency in different ways. We're going to look at one more, and don't worry, I'm ahead on time, so we will get to lunch. We will look at one more concurrent language, one more language, and then we'll close. So the final concurrent language to look at is Clojure. And Clojure is unique from these other languages because it is Lisp-based. And the founder of Clojure wanted it to be robust, practical, and fast. And he wanted to get away from all the locking problems. And so he just said, hey, everything is immutable. Clojure has immutable data structures. Once something is created, you cannot change it. Hey, no locking problem. no channel is going to change a variable something else is using. They can't change it. So that made that quite easy. But Clojure is kind of unique because it was built on the JVM, because the founder wanted it to be a part of an ecosystem that was already alive and thriving. But it's also Lisp-based because he liked, Lisp and some of those things. So you have almost kind of, I guess, a good and a bad thing. Like, and I'm sorry to state it in those black and white terms. It is not like that. But so JVM is obviously something that is established and people know it. Lisp, not so much, right? Most people, I think we are very comfortable with C-based languages. Lisp is a little bit more rare. So I think that is maybe one of the hindrances to its adoption on a larger scale, but it is gaining steam. People do like Clojure and how it does things, so, it can overcome. So expressions in Lisp. Everything within parentheses are a self-contained expression. And the order of operations is that the function goes first, or that expression goes first, and then the variables or whatever that the function acts upon are second. So it's a little bit like reading left to right, maybe. Now, one cool thing about Clojure is that the operations know the most efficient way to do that operation on whatever data structure they're being called upon. So this is an example of, this is called a vector in Clojure. We won't go into the details of a vector, but essentially it is a list-esque, array-esque thing. It's a sequence, and you can add things to it. And then this down here is a list. And a quick note, this apostrophe merely states that this parenthesis is not an expression, right? We just said Lisp, everything in parentheses is a self-contained expression. However, not this. This lets Clojure know, wait, this is not an expression, don't evaluate it as one, it's a list. So that's what that is. Anyway, so this method conjoin, you can call it on a vector and you can call it on a list, and it will operate differently because the most efficient way to add an item to a vector is to add it onto the end, so it does that. And the most efficient way to add an item to a list is to add it onto the beginning, so it does that. So Clojure kind of takes some of this legwork off of us and does things efficiently based on how the language is implemented. Clojure also has this really neat thing that is the different ways you can chain something. So they have thread first and thread last chaining. And as you can notice, the only difference is thread first has one arrow, thread last has two. So it's a very slight difference in how it's set up, but then how it changes is a thread first system will take the evaluation of each expression and add it into the second place, and then evaluate this. And then we'll take the result of this expression, add it into the second place, so now this will be our first argument, and we'll evaluate this expression, and it goes like that. The thread last chaining, which is more useful on things like a filter or something, will take the result of the expression and add it into the, the last place. This always trips me up a little bit, but it's cool, right? So then, this expression will go here, but it's sort of like reverse recursion or, something like that. So we actually start with the last expression and evaluate that in the first position and then go on like that. One of the bad things, as mentioned, with Lisp is you can have a lot of parentheses. That is something that it inherited from Lisp. But overall, the power and the efficiency that Clojure brings makes up for this in spades. And so people really do enjoy developing with Clojure overall. Now, to close out, we are going to talk about everyone's favorite language. I know this is the back-end track, but I know we have all most likely at least seen some JavaScript because it is everywhere, right? It is the language of the web. So JavaScript, as you may or may not have heard, was written over 10 days. And it was written over 10 days because Netscape, the browser, wanted to create a language for the web, but they wanted it to build off of the popularity of the name Java, because Java at the time was a very popular language, and so Netscape wanted to take that. And so Netscape and Sun, the people who own Java, devised a trade. They said, you can use the name Java. In exchange, we want you to enable Java applets in the browser. So that's how we got Java applets in the browser. So then JavaScript was written in 10 days and then implemented into the Netscape browser over 6 months. This explains many of the early and frustrating challenges that a JavaScript developer may run into. JavaScript doesn't have very many opinions. It's even more extreme than Ruby, right? However, this is useful in JavaScript and necessary. And why is that? It's because there are lots of browsers. So JavaScript has lots of flexibility, and then more flexibility. And the reason why is because so if you program in a base programming language, your Python, your C, your Rust, whatever, and then you maybe create a package, and someone needs to install that on their operating system, you might have to allow for different operating systems, and you maybe include those in the package, right? And then the person installs it, and everything works. However, JavaScript not only has to deal with different operating systems, it also has to deal with different browsers and any combination of any browser on any operating system. So you need this flexibility in JavaScript, as much as it may have caused some pain. You need it because the browsers are always different. And the browser wars are most definitely a thing. I'll have an example for that in a second. I wanted to quickly point out, though, that in JavaScript there is no sleep function. You may be familiar, especially in Ruby. A lot of these ended up in my Ruby tests. But you can't tell JavaScript to sleep because then the browser would crash, right? There's one thread of JavaScript, and if you kill it, well, you don't have a website anymore. So fun fact that you may or may not have noticed going through. And JavaScript also has this fuzzy equalization, right? So 5 does return true if you set it double equals to a string of 5. You think, wait, that doesn't make sense. It's not the same. Well, it's not. So if you do triple equals, then it does return false, as you might expect and you might plan for. And then, of course, 5 is triple equals to the number 5. So in JavaScript, this double equals was added again for that kind of flexibility, but it's now very much accepted best practice. We always use this triple equals because we are working on improving JavaScript. It is growing up. It is wonderful. ES6 was a whole host of new things. So we had this foundation, and now we're building on it. And how this can relate to the browser wars is there's actually this funny bug. In the Firefox browser, if you want to add 2 decimal points to the end of a number, or 2 zeros after the decimal point, you cannot. Because that doesn't make sense, right? You don't need 2 zeros after a decimal. Now, there has been a bug ticket open with Mozilla to fix this because people work with currencies and they want to use straight numbers and then display those. But Mozilla has maintained, no, we're implementing numbers correctly. This is not a bug. We do not need to fix this. Now, Chrome and Safari, though, of course, they do allow those numbers after, or the floating zeros after a decimal. So this is an example of how there are a lot of, the browsers will always be different, and they will always implement things differently, and we need to retain some of this flexibility in JavaScript because the internet needs to work for everyone, right? And arrays are everything you'd ever want in an array. You can add stuff to the end, the beginning, take stuff away from the middle, access by index, do whatever you want. Again, that flexibility of JavaScript, it doesn't care what the name says. It makes its own rules that work within the web. And another thing is that everything is mutable. And everything has to be, because the web is always changing, and you may need to change any variable at any given time to do what you need to do. So now is where the spoiler alert comes into play. If you have not seen Game of Thrones, or you have not read the books, and you do not want to be spoiled, please leave now, or close your eyes, cover your ears, because now we are going to compare these languages to their alter egos in the Game of Thrones universe. And the first one of these is that the true king are these Lisp, Java, and C languages that really control everything we do. All of the languages we talked about are based on one of these. So, sorry, you can't escape. Now, I was thinking about Ruby, and I thought, okay, well, Ruby is magical, and she wears a ruby, so that makes sense. But then I thought, but Ruby is really fun. They make bongs out of hair dryers. Like, how she's, she creates things, but is not necessarily a party to be around so much. So who has magic and also likes to party? We'll go with Thoros of Mir for Ruby. Now, Python was a little bit similar, because Python 2.7 is very different from Python 3+, right? There was a lot of breaking changes. And so, but Python 2.7, Python still has this underlying, hey, we're going to state the rules and mean what you say. But then Python 3, you got to do async stuff, so you got dragons. And then Erlang, of course, you have concurrency by multi-threading, right? And JavaScript has so many faces. And Clojure has immutable data structures, or immutable oaths. When you say it, it sticks. It never changes. And Rust is the world takeover you don't see coming. It's going to happen. And of course, our last one is Go values speed above all else. So Go is the entire 7th season. And I am right at 40 minutes, so if you have questions, please come find me at lunch. I would love to talk more with you, and have a great rest of the conference.